Thanks and welcome to my talk today. As Ismail mentioned, I left academia and I'm now an engineer for hydropower restoration project at IUB Engineering. But I will talk today about my PhD project, which I concluded at ETH Zurich within the Fit Hydro program framework. So in this project, I developed curved bar-rack bypass systems for the protection and the guidance of downstream migrating fish. So one solution to protect and guide downstream migrating fish at hydropower plants are mechanical behavioral fish guidance structures, such as louvers or bar racks. These structures are placed in front of a turbine intake with an angle to the approach flow of typically 10 to 45 degrees, and with the bars angled to the approach flow of 45 to 90 degrees, with a bar spacing of 25 to 100 millimeters. So the orientation of the bars to the approaching flow create flow separation at the bar tips and high velocity and pressure gradients in front of the rack and between the bars, which are perceived and avoided by approaching fish. Due to this angle of the rack to the approach flow, the parallel velocity component guides the fish towards the bypass system and carries them safely downstream. So while the fish protection and guidance of louvers and classical louvers and bar racks can be quite high, they have a lot of disadvantages for power plant operation and energy production due to high hydraulic head losses and an asymmetric downstream flow field. This is why hydropower plant operators are still hesitant to apply this technology in the field. So during my PhD, I developed a new curved bar shape to apply for these fish guidance structures and tested this new bar shape in the laboratory to evaluate the effect on the hydraulics and the fish behavior. The laboratory test showed that the hydraulic head losses could be much reduced by this curved bar shape. So as an example here, we can see different mechanical behavioral fish guidance structures. And let's say we have a rack that is angled at 30 degrees to the approach flow with a bar spacing of 50 millimeters. And we take the hydraulic head loss coefficient as a proxy for the hydraulic head losses. And the tests show that with the curved bar shape, we can reduce the hydraulic head losses by a factor of 20 compared to the classical louver, and still by a factor of 4.2 compared to the bar rack with these straight bars. So this means that the hydraulic head losses are now in the same range as for typical intake trash racks, which are already installed at each hydropower plant. And the reason for the significant head loss reduction is the flow straightening effect, which is produced by these curved bars. So here we see the flow fields of an angled bar rack on top and of a curved bar rack on the bottom. And this is the result of a 2D CFD simulation, which was conducted by one of my former master students. And we can see that the downstream flow field is quite symmetric due to this flow straightening effect of the curved bars. And we have a gradual velocity increase towards the end of the rack, where the bypass would typically be placed upstream of the rack, which is advantageous for fish guidance as well. So after optimizing the hydraulic performance of these mechanical fish guidance structures, we wanted to find out how the fish would behave around these structures. And to this end, conducted a series of live fish tests at the prototype scale model in a large laboratory flume with an adjacent open channel bypass, as seen in this photograph. Recorded the fish behavior with these submerged cameras. So we tested 6 different fish species, so different cyprinids and salmonid and the European eel under 4 different hydraulic conditions, varying the mean approach flow velocity between 0.5 and 0.7 meters per second, and the bypass entrance velocity, which is classified as a ratio between the flow velocity right at the bypass inlet to the approach flow velocity, which was chosen between 1.2 and 1.4, as it is recommended by the US Bureau of Reclamations. So from these tests, we could define the fish guidance efficiency, which is basically the number of fish being guided by the curved bar rack and swimming into the bypass, divided by the number of total fish that were actively swimming around. And basically, what the tests show is that the fish guidance efficiency, so the success rate, was over 85% for all the cyprinids and the salmon pars, but it was lower than 60% or around 60% for the eels and the brown trout. So there's still some room for improvement for these two fish species. In the next step, we wanted to quantify the effect of the flow conditions on the fish behavior, and therefore conducted 3 binary logistic regression models. And from this statistical analysis, it became obvious that the approach flow velocity, as well as the bypass entrance velocity, are significantly affect the fish behavior. So this means that higher guidance efficiencies were achieved for higher approach flow velocities, and higher guidance efficiencies were also achieved for lower bypass inflow velocities. And this first result, we wanted to have a closer look at, because this basically means that the curved bar rack has a higher behavioral barrier effect for higher approach flow velocities. And to verify this hypothesis, we had a closer look at the hydraulic cues in the vicinity of the rack, so between the bars and at the bar tips. And for this, we set up a 3D CFD model and analyzed different hydraulic cues. So here on this figure, you see the spatial velocity gradient. So that means the change of velocity over a certain length around the bar tips and between the bars. And you clearly see that the spatial velocity gradient is elevated, is higher between the bars for the higher approach flow velocity, which verifies that the behavioral barrier effect of the rack is higher at higher approach flow velocities. And basically the same result can be obtained when we model the pressure gradient, which is higher between the bars for higher approach flow velocities. So to demonstrate you the fish behavior at this curved bar rack in the laboratory, I have here a video, I hope it works, of 3 nays. These were actually the smallest fish which we tested. They're only 7.5 centimeters long. And you can see their behavior in front of the rack, and you can see their reaction to the elevated velocity and pressure gradients. So they avoid swimming through the rack, even though they could easily pass between the bars, and they are successfully protected and guided to the bypass. So to summarize, in this study, I developed a novel curved bar shape, which greatly improves the hydraulic performance of mechanical behavioral fish guidance structures. The curved bars lead to a flow straightening effect, which leads to a symmetric turbine admission and to 4.2 times lower head losses compared to straight bars. The live fish tests we conducted proved the behavioral barrier effect of this kind of fish guidance structure. And these results show the large potential this guidance structure has to protect fish at hydropower plants with minimal impact on hydropower operation and production. And the numerical model that was developed in this study allows now for a further optimization of the bar shape for any specific hydropower plant. And this was actually already done for a hydropower plant in Switzerland, where this new bar shape was developed. And the project has just been given to the authorities to check over, and if they approve, the first curved Barak bypass system will be constructed in Switzerland in a couple of years, hopefully. So with that, I thank you very much for your attention. If you're interested in more information on the project, you can download my PhD thesis on the ETH website, or you can contact me anytime by email. Thank you.